Snakes and Ladders is a game played using a board, a piece, and a die. To play this game, you roll the die and you move the piece according to the result of the die. Your goal is to move to the last square of the board in as few moves as possible. During this process, whenever you land on the bottom of a ladder, you move to the top. Whenever you land on the head of a snake, you move to the tail of the snake. As you can notice, in this game, you make no decisions, which means that this game is completely based on luck. We want to find out the probability of winning the game on a specific number of moves. To calculate this probability, we can use simulations. We simulate the game a few 100,000 times, and we can estimate the probability of winning in a specific number of moves by dividing the number of games won at that specific number of moves by the total number of games simulated. This is my design of the game in pseudocode. We first store the current tile, the number of moves, and whether they've won. We increment move by 1. This is my design using pseudocode. We first store the current tile, the number of moves, and whether they've won. For each move, while they've not won, we increment move by 1. We roll a die, and we move according to the die result. Now here we check whether they've won. If they have, we skip to the end, and the loop is broken, and we return the number of moves taken. Otherwise, we move the piece again according to the board tile that the piece had landed in, which can either be a snake, a ladder, or nothing. Here's my implementation using Python. This function is the same function that we previously shown using pseudocode. Here's the function that runs a number of games, and we calculate and we count the number of successes, which is matching the moves taken. And we divide that by simulations to get the probability of winning on that specific move. Here's how we calculate the probability distribution of a range of moves. We first have an array of floats. We run the games a lot of times. Each time, we add 1 to the result where the index is the number of moves taken, and the result we track how many games take that number of moves to win. Lastly, we divide each value of result by the total number of simulations to get the probability. Here we return the result. This function is the same as this function. However, it distributes the simulations into multiple processes by using pools. Here I have done the same thing but using NumPy, which makes it a bit faster. Here's how I've modeled our board. In the generate board function, we take in the length of the board and a dictionary containing the tile and where that tile leads to. Result of simulating the game 100 million times. We can see that the probability of winning is highest at around 10 moves. However, there's another peak at around 20 moves, which means that when you play the game, you're probably gonna win in less than 40 moves. Still, the probability of winning in the most likely move is still very small. This is 3.5%. And we can see that as the number of moves get bigger, the likelihood of winning in that number of moves gets smaller by each move, but never zero. You can see that there is always something here.